Thank you very much for the introduction and the opportunity to present. And thank you again, Molly, actually, for all your coordination. Much appreciated. So by the title, I'll be talking about microwave plasma processing of natural gas and its conversion, not just to hydrogen, but value-added carbon materials. We'd like to acknowledge coworkers, collaborators on this project, HQuest in particular, for their pilot scale facility access, use, and analysis of the materials, which is what this talk will be about, and in particular, George Skopskaw, President and CEO. This work was supported through an NETL, used for, you see the acronym down below there, collaborative agreement. Let's see. All right. So in terms of brief outline, I'll talk a little bit about relevance to hydrogen generation for the microwave plasma decomposition, TCD, if you wish to call it that, but it is plasma driven rather than thermal. And then talk a little bit about the results from, well, the conversion of methane to two forms of carbon, nanographene and a graphitic carbon black analog. There's the acronym GCBA. And I'll briefly describe a little bit about the characterization of the carbon materials through various characterization techniques, spectral diagnostics, electrical conductivity of the carbon, and briefly conclude. So by way of background, certainly TCD, thermally driven methane decomposition, is one way route to hydrogen. Hydrogen itself is an energy carrier, tremendous amount produced worldwide, mainly from reforming of fossil fuels. It is an energy carrier, and certainly in the States, and the preferential process is steam reforming of methane, SMR, a process that produces considerable CO2, consumes considerable water, and has high CO2 footprint. Carbon black manufacturer carries similar environmental impacts. In contrast, microwave-driven decomposition of methane does not generate CO2. There's no water used in the process itself, so there's no in situ CO or CO2 that requires removal. No water gas shift reactions required either. It is in that sense a plasma-driven pyrolysis process, but it does provide then, if renewable electricity is used, for coupling the electrical energy storage into chemical bond energy. It does not require a catalyst, but in fact produces solid carbon, a carbon that has a purity as high as that of the incoming feed natural gas. Therein, it would be suitable as anode or electrode material for batteries and or supercapacitors, but the microwave technology itself opens other possibilities for chemical synthesis, actually in an integrated process. Just to make mention of HQuest microwave pilot scale microwave reactor, it is based on design simulations. There are many variables that including gas flow, concentrations, energy, for example, but a unique factor of, or feature I should say, of their reactor is the high optical access. You see a couple illustrations of that. One is a very large optical viewing window on the left, as well as multiple viewing ports on the right, both of which allow not just the optical access, but then for that access allows for species and or temperature measurements. I'll touch on that in a minute. In terms of the controls, this is a larger scale facility than what would be have in a laboratory facility. So there are many reactor controls, concentration, flow rate, and or power, PCF. And through a design of experiments, that's what the DOE acronym is there, design of experiments, one can translate operationally product metrics such as yield, selectivity, uniformity in terms of reactor controls. But since those reactor controls do translate into reactor conditions, such as temperature, again, concentration and residence time, the design of experiments can be interpreted in two ways in terms of product metrics upon reactor controls for an operational understanding, or in terms of reaction conditions for a fundamental understanding. Shown on the upper left is just an earlier version of the microwave reactor with the product coming on out, but quite hot actually, and that's why the luminescence there. But what you're seeing is high, this is again a much earlier configuration, different design, but it does illustrate the high optical access provided, which in this case provided allowing for temperature profiling throughout the entire flow process through the microwave-driven reactor. Two types of spectral diagnostics that we have focused on have been, number one, black body emission from the carbon for monitoring the temperature of the reactor, and you see that listed here is 1600, versus more detailed, higher resolution spectral emission scans such as over the C2 band, from which we can infer not only a temperature non-equilibrium, as you can see, of that radical species, but also make the inference as to the concentration of some of the radicals as well. Just to illustrate the different forms of the carbon product that are produced, these are 3 TEM images illustrating again at the length scales shown on the marker at the bottom of each image. And what you're seeing in the TEM image is part of the lacy net mesh grid in each image. That's kind of the webbing that you're seeing. But these are the 3 nominal forms of carbon product produced by the microwave pyrolysis of natural gas. Most interesting product is that of the nanographene. You're seeing that as crumpled layers. Many of them are somewhat concatenated together, something like a Russian doll from that concept. But many are wrinkled, few layers stacked nanographene, versus a more product that is somewhat more amorphous or maybe more graphitic, both resembling carbon black. And you can see that there's a strong difference in the internal structure within the particles on the lower image on the right. They're not uniform contrast nor filled uniformly within, but there's a considerable amount of semi-graphitic structure within those particles. Just to give a little bit better resolution, higher contrast for the 2 products of interest, again, the nanographene, you can see multiple sheets, crumpled, folded. Much of this is probably due to our processing anyway for the deposition on the grid itself. So this is not necessarily totally inherent to the process. But what is inherent is that it is few layer graphene. You can see on the right-hand image, the number of steps of the image, number of layers offset from one another. And so these are very highly crystalline materials by selected area electron diffraction, which I'll come to in a few minutes. The other desired product of interest, and I'll tell you that why as well, is this graphitic carbon black analog, again, the acronym GCBA. But there's a considerable amount of internal structure, and if you look closely, you can see that there are graphitic lamella outlining the perimeter of the particles. So in other words, they're encapsulated by rather noticeable graphitic ribbons or shells, if you wish to call them that. So I mentioned the design of experiments. I'll only show you for the time here just a couple snapshots of results in terms of the methane to argon ratio for a low methane argon versus a high methane argon ratio, in terms of the differentiation in terms of either reactor conditions or fundamental conditions for the products that are then produced under those 2 ratios. So under low ratio, there's preferential production for a mixture of nanographene. You're seeing all that here, along with a graphitic carbon black analog, again, the internal structure being the differentiator for why we call it graphitic, versus under a high methane to argon ratio, where there's in fact, a relative absence of graphene versus more exclusive production than of this graphitic carbon black-like material that is seemingly heat treated, shall we say. So again, just highlighting and contrasting the 2 products produced in the aerosol phase, and that's why the term freestanding, you might hear as well, produced directly as an aerosol. So that is also quite surprising when you think of combustion and other types of pyrolysis processes, that you do not necessarily form nanographene as a freestanding aerosol by the direct particle nucleation, speaking to why the plasma is somewhat different in that regard. Versus again, the graphitic carbon black analog, just again showing the outline of the graphitic lamella on the particles themselves. Again, these are highly overlapped, merged, somewhat fused in a compact fractal aggregate. So we've taken XRD spectra of these materials produced under the different conditions. You're seeing that here. The reason so this would be under a low methane argon ratio with then deconvolution applied to that main peak. The peak on the right is just an expanded version of that on the left, just over a smaller angular range, applying a 2-peak deconvolution profile once the background is subtracted to identify 2 phases, if you will, of different forms of sp2 carbon both. We've also applied Raman spectra to the product as produced under the 2 nominal methane argon ratio conditions. Again, the low ratio producing a mixture of the nanographene and graphitic carbon black analog versus the other condition, producing exclusively the graphitic, or why you're seeing CCBA, sometimes we have referred to it as conductive carbon black analog. I'll get to that as well. But there's a considerable difference, as you can see, in terms of the lamella length, referenced by the ratio of the D to G profiles, as well as the 2D signature peak presence or relative absence, although not totally disappeared, under the high methane argon ratio. But there's considerable distinction between the different products by XRD and Raman. One way we have used, one method we have used, namely TGA, to assess the relative phase fractions, the relative contents in the product of the two forms of sp2 carbon, has actually been by TGA. So what you're seeing on the left is a thermogravimetric spectrum, that being then the black line, and the blue then being the derivative of that. And you can see that there's certainly a shoulder on the left. In fact, this TGA does suggest that there are two different forms of carbon with different thermal oxidative reactivities. And in fact, those two different forms correspond to the lower peak, the nanographene, versus the higher temperature peak corresponding to the graphitic carbon black analog. How do we know that? Well, we've done comparative TGA and or derivative peak matching using different reference materials. The graphene is not shown here, but what is shown on the plot on the right is for oxo-noble, a well-known commercially conducting carbon black. The product name is shown there basically, but we can, by reference materials, assign these peaks to the right form of the sp2 carbon, in this case, the higher temperature peak being assigned to that of the graphitic carbon black analog, based again on the reference. The reason we're using that oxo-noble as the reference, although the contrast between these two TEM images, upper and lower, is a little bit different magnifications as well, you can see that there's considerable internal structure within the particles of both carbon forms, namely the microwave produced carbon on the right, conductive, very internal, high degree of structure, shall we say, internal, and ribbons external, versus that of the oxo-noble. They are quite similar in that regard, as also manifested then by this overlap between their derivative TGA spectra. So in terms of compilation for the different parameters for the crystallites, under the low methane argon ratio, again, there's a mix, comparable mix of graphene, nanographene, and conductive carbon black analog. In terms of the lattice parameters, you can see that there's significant stacking of the crystallites. The interlayer separation, however, is, yes, a little bit larger than that of graphite itself, suggesting turbostratic stacking in most cases on an average, as well as the L sub A not being able to then differentiate based on the 100 peak, resolve the two forms given overlap of that peak. There's just a combined composite value net given then for the in-plane lattice dimension L sub A. But again, roughly based on the TGA derivative spectra as assigning fractional forms, fractional content to the mixed product form, the two forms, graphene, the carbon black, analog, occur roughly in a 1-to-1 ratio. The TEM images for your reference are shown below. The crystallite geometry, again, shown in the upper right, as well as the difference between low ratio and high ratio methane to argon for the two cases, red versus blue, illustrating the capability to tune, if you will, and or select which product by reactive condition. Again, it's a short talk, but I'll just mention another thrust or direction dimension, if you will, to that design of experiments methodology. In this case, it was exploring the the hydrogen to methane ratio. Under 3 nominal reactor conditions, A, B, C, each with a monotonically distinctly different higher hydrogen to methane ratio, you can see that the XRD peak as of the bulk material, solid carbon produced, shifts not only in terms of angle, but also becomes much more preferential for one main peak, that being actually then of the nanographene. In terms of the selected area electron diffraction, with increasing hydrogen to methane ratio, not only does the phase fraction, that is to say content of nanographene increase, but so too does the quality. And you can see that by the selected area electron images shown left, upper on the right, upper and lower. As I made mention, we have sometimes referred to this material produced by the microwave plasma decomposition as a conductive carbon black, not just a graphitic carbon black. The reason for the conductive acronym as well is that we performed, not surprisingly, electrical conductivity measurements, given it would be suitable as electrode material. And we have compared that material mixed, nanographene plus the conductive carbon black analog, compare that material mixed to that to XC72. And so the way we have measured the electrical conductivity shown in the upper panels, where we have made pellets of the material, sputtered gold for electrical contact, measured the resistance, calculated the conductivity, and relative to XC72, another well-known commercial conductive carbon black used as an additive for batteries and capacitors, electrodes, the mixed material actually has a superior electrical conductivity. And so in terms of summary, next generation hydrogen technologies could enable use of stranded domestic energy resources, such as stranded natural gas reserves rather than flaring, for example, in a modular concept. Certainly, plasma itself as a way of generating hydrogen provides a way of diversifying hydrogen feedstocks. Hydrogen itself has many present-day uses, has a high environmental footprint for its SMR production presently, and the carbon materials produced would have many applications, notwithstanding that for battery electrode applications, as well as many other conducting additive applications, polymers, composites, etc. So I'd like to acknowledge HWEST for their collaborative work on this project, the opportunity to participate in the USFR coalition, and their microwave scale process is scalable, and it also provides then the opportunity to deal with or process a wide range of feed compositions along with variable energy input, producing a number of products. Again, it's a platform technology here only demonstrated for the production of hydrogen and solid carbon in two forms that I've shown you. But nonetheless, there are attractive economics and environmental footprints associated with the process as well, as I described at the beginning of the talk. And with that, I may be nearing the end of my time. So thank you very much.
Great. Thanks so much, Randy. Really interesting talk. We already have a couple of questions in the chat. Again, for those joining, it's on Slido. So Greg Smallwood asked, when optimized to produce few layer graphene, what is the fraction of particles that are few layer graphene? And he says, as a reference, University of Duisburg, Essen has greater than 90% FLD.
So under the low methane argon ratio, roughly, I'll say a 1-to-1 ratio, nanographene GCVA material.
Okay. And is that, are you optimizing for that, or are you seeking conditions that would seek to maximize few layer graphene, or are you looking more at the conductive carbons?
That's a great question. Thank you very much. From the standpoint, in other reactor conditions, and actually one of our previously published papers actually with this, we have had much higher nanographene contents. I can't speak exactly to the exact percentage, but they have been far higher. And other reports in the literature also suggest far higher percentages of nanographene in a form as a solid carbon. These conditions and processes under which it is formed are, well, I'll suggest highly non-equilibrium. And so depending upon, there are many couple parameters in terms of plasma intensity, concentrations, residence times, governing that relative phase fraction, if you will. But to your question, which is better, which is preferred, while the nanographene pure might be highly desirable, it's not clear that that's necessarily the most practical form of the product. Speaking somewhat more generally, the carbon black industry works often very closely with their customers, for example, for rubber, plastic, conductive applications to tune the product characteristics for mixing, compounding, and all such characteristics. Having graphene as a fraction to something that resembles a carbon black in terms of processing and characteristics might be an easier inroad for that displacement, shall we say, rather than the complications of a new form with different mixing rheology characteristics.
Great, thanks, Randy. So to summarize 3 questions in a row, or at least parts of them, an overarching question is, what is the pressure of your system? Is it atmospheric or is it high
Atmospheric.
pressure?
Atmospheric. There's probably a slight overpressure since the gases are being fed, but roughly atmospheric.
Great. And then Riza asked, do you have TEM images for the different hydrogen to methane ratios? Does more hydrogen promote formation of graphene sheets? I think you spoke to that, but maybe just expand a little bit more on that.
Yeah, so in previous work, not shown here, sorry, we do have a publication on that, but in previous work, we did actually look at the hydrogen to methane ratio and did publish TEM images for that progression along with other characterizations as well. But the relative fraction of graphene and quality both increase with increasing hydrogen to methane ratio. It may not seem necessarily intuitive chemically why that's so, but there's certainly a practical motivation for looking at that as well, because if you're not converting to 100%, if your methane conversion is not to 100%, whatever process you would do to then feed back some of your methane will likely carry over some of the hydrogen of your product. So having that hydrogen as an input feed gas is not a stretch, and actually has some logic to it from the standpoint it's going to be your main product. It's easy to recycle some of that back to tune the gas composition to that producing best carbon, for example.
Great. And one final one from me, having run microwave atmospheric reactors myself, I know one challenge is that the carbon buildup on the walls of the reactor will disrupt the process as it absorbs kind of the microwave energy directly there rather than getting the gas. And so do you have that problem? And if so, what's your injection strategy? So do you inject the methane through the microwave region itself, or do you inject it downstream in the kind of effluent of the plasma?
And so you're exactly right. I think the pandemic problem, sorry for the word, but the universal problem, I just had to do that, but the universal problem with quartz tubes as a reactor confinement, even given the microwave transparency, is in fact at some point with hydrocarbons, you'll wind up with some carbon deposition, and then it becomes a susceptor, local heating of the quartz, it'll blow a hole in the wall. This reactor, as I showed on the earlier slide, is an all metal cavity design. There is no quartz. It's an all metal cavity and far larger than the usual diameter for quartz tubes laboratory scale. So there is not a carbon coating, carbon deposition. And even then again, it's a metal reactor. They do have the capability for different gas injections in terms of co-feed or supplementary feed somewhere within the plasma, or even other fluidized type bed arrangements as well. So it's a much larger scale, somewhat free from those other encumbrances as often encountered.
Great. Thanks, Randy, for that very interesting work. And thanks once again for joining us today.
Thank you.